Good morning, good evening, good whatever the time is where you are. Today we're going to walk through a power anomaly detection dashboard that I've created with the aim of trying out different anomaly detection models to look into voltage data, mock voltage data coming from smart meters. So these are essentially what we're trying to do here. Grab mock data created based on real data. So I currently work for a company in the Netherlands called Aliander. They are one of the network maintainers for the electricity grid. And my main role at the moment is looking into being able to get data out of electrical smart meters to see how they're doing, whether there have been outages, if anyone's doing energy fraud, for example, stealing energy, where problems are occurring in the network based on what meters have data and what don't, for example. And so I thought it would be a fun project to look into possibly using various different machine learning algorithms to see whether or not we can programmatically look into anomalies coming from time series data. So that's the general outlook. The main reason that this is interesting, though, is because we are using something called Trino as a means of interacting with streaming data, in this instance Kafka, and database data, tabular data, in this instance Postgres, in the exact same SQL language using this layer of Trino. So that, to be clear, is the crux, the interesting part of this, and the practical demonstration is just to make it a bit more spicy, you know. I could just talk about Trino, but where would the fun in that be? So here's the general pipeline that we'll be going through. Using Docker with a Docker Compose file. Here we have our general overview of what the Docker Compose, the Docker architecture looks like. So running locally, I have a Docker daemon. I'm not sure if I'm saying that right. I'm grabbing images from an images registry and then running them as containers based on this Docker Compose file. Docker Compose is just a means of creating a standardized YAML to do all of these like separate commands. So just, that's me. So just to whet your appetite a little bit, this is then how that would look like. So we're pulling Zookeeper, we're pulling Kafka, we're pulling Trino, and we're doing some stuff. Cool. Yep. So in this instance, we don't really have too many Docker commands because the thing that we'll just be using is Docker Compose up, basically, which is then do whatever it says in that YAML. And by the end of it, we should have our 5 separate things running in Docker. So Postgres, a Postgres database running in one Docker container. Kafka, which is then our streaming software, a means of having an overview of where our Kafka messages are going. Red Panda is just, at least what I'm using it for, is just an interface to keep track of the messages. And similarly, Zookeeper is being used here to collect all the metadata on the different Kafka thingies. Oh, I've completely ignored my slides. This is why you need to write a script or have a better memory, one of the two. Where were we? So this is, for those who don't know too much about Postgres, this is how Postgres databases are structured. Essentially, you have a large database cluster. In this instance, it's a pod in Docker. Container in Docker, excuse me. There are X amount of databases within this cluster. In this instance, I'm only using one. You have X amount of users. I will be using again 1 because this is just a demo. And then within each of these databases, there is this overview. So this is then based on a schema, and then you have tables, indexes, views, X amount of different things that you can do with Postgres. So just to be truthful, we have our Postgres database. Oh, by the way, this is DBeaver. You don't inherently need it for this tutorial, but it's a nice way of having a graphical user interface. I will show you the commands that you can do in Trino as well to get the same data, so you don't inherently have to download this. But in any case, we have our public schema, and within it we have then the tables. This is the table that we care about most. This was just to make sure things were functioning. Various different views. Basically all of these you don't need to worry about for this demo. We're only using tables, but you can get more out of Postgres than what I will be demoing here. The procedures, for example, are means of creating standardized functions and means of interacting with your Postgres. Your Postgres tables whilst being in Postgres still, essentially using SQL to run a function, basically. So that is a quick, cheeky overview of our Postgres setup. This is an overview of how Apache Kafka works. Essentially, the idea of Kafka is that you have a big broker. Think of it kind of a bus where you shove things in at one end and then consumers pull them out at the other end. The producer will just keep adding messages to this broker, and then it will split them up over various topics. In this instance, we only have one topic, so you can ignore topic 2 and 3 if you like. And to make sure this, to be clear, this is fully distributed, so there are partitions within all of the topics. And this broker then makes sure that the topics with all of their partitions are not overlapping with each other. It's a mixture of a Kafka and then also Zookeeper that then checks that all of the different messages are that they're not read twice, for example, that they are not that there are no duplicate there are no duplicately produced messages in the topic. So in this partition there will never be the same message in 0 and 1, let's say. So it's a mixture of the broker, which then keeps track of all these things, but then in this instance we're using Zookeeper to maintain this distributed system. So then this little guy. And Red Panda, I never thought of the example for Red Panda. Basically it's just a graphical user interface to check that your messages are coming through. That's what I'm using here, and it's also nice to kind of add a bit more user interface where possible. And of course, the star of the show, Trino. Trino is essentially a layer that sits between all of our different data sources. So in this instance, this is PostgreSQL and Kafka. It has a client and the front end which you then interact with, and then based on what you request Trino to do, the Trino cluster will then coordinate, i.e. pass, plan, and schedule the request that you make, send it to different distributed workers. At the moment we're only using one, so this is not as complicated as as this image would suggest, but you can scale this as horizontally as you like. And then based on what you've requested, so let's say it's a select all from Kafka, it will then pass, plan, schedule that select statement, put it through all these workers, and then get the data request that you want, and then pass it all the way back through to the client again. So that's that. And the fun thing about Trino is that there are so many different connectors that it has. For the full list of connectors, you can go to their website. However, like broad strokes, there are connectors for your regular databases, so Postgres like we're using, mysql, Oracle, various other SQL databases. for the newer and up and coming places, you've got stuff like BigQuery and Snowflake. Sorry, BigQuery and Snowflake, and I think this is Fargate, maybe. Not sure. And then is that Databricks? No, being silly. Whatever. The data platform people, Snowflake, I guess, is the big one, at least where I'm concerned in my field. You can connect with data lakes fairly nicely using Hive as a method, or what's this called? Iceberg, is it? Yeah, Iceberg. Just a means of looking at very large data sets, then based on like this flat structure. So using Parquet, or some people use CSV or Avro or whatever. Doesn't really matter in this instance. And last but not least, all of our NoSQL favorites. So Elastic and is that Mongo? Not very good at the so Elastic and MongoDB and whatever NoSQL things we've got going. Nice. Cool. So that's the general overview of the kind of pipeline-y setup. The data that we'll be playing with is taken from like actual smart meters, and then to mask, to make mock data from this, I trained a random forest regressor with a lag 1. So we end up with data that looks like actual data but isn't actual data. And then that will be streamed in through Kafka to Trino, and then it will be plotted in the front end using streamlit. So streamlit and plotly, two different Python dashboard things. And we'll be talking with the Trino layer in Python using something called SQL Alchemy. This is a ORM, or Object Relational Management System, I think. Ugh. Yeah, mapping, not management. Object Relational Mapping System. It's converting data, as it says, to OOP language. So we will be talking to SQL in Python using this Python package. It's a quick summary. Our anomaly detection models are a set of River for time series, yes, online machine learning in Python, but it's specifically, where are we? It's specifically the anomaly ones. This isn't what I want. In any case, there is a module in the River package. I don't want to go to GitHub, it's falling apart. This is why you don't do things in the evening. In any case, there are two that are being used from these guys. The Gaussian square and the half space trees, which are essentially just time series versions of fairly well-known anomaly detection models, but taking into account the fact that it's based on time series. And then the more known approach of using sklearn, looking at different outlier detection models. So we also have included this one class SVM. This is always a nice overview. This is the thing that sklearn does really nicely, is they have nice pictures of how their algorithms work. So essentially here, orange is non-novel data, i.e. the ones that you think are fine, and then the blue ones are the outliers, and the lines are the algorithm, essentially saying everything that's in this area we consider regular data, and everything outside of it we consider a anomaly. Various different data sets. You can see then how the anomaly detection systems are working. So for us in this, we've included one class SVM, which is a support vector machine. Also local outlier factor. Yeah, we don't have the lines as there's no predict method, so there you go. And I think, did I include isolation forest? No. SVM, local outlier factor. Oh, and this other one that's not included in this plot, the elliptic envelope. So in total we have that plus a hard cutoff one, just to see as a baseline to compare. So basically, if the time series goes above or below, if the time series goes below a hard cutoff, then we're considering that also as an outlier. Cool. So this was trained on some samples of the data, and then the actual data that will be considered an outlier or not is streamed using Kafka via Trino through SQL Alchemy to our front end. And then also in the front end, I've included a means of manually adding anomalies so we can then see how our models catch them online. Whew. So there's the general overview. Let's quickly go through the setup of how you do this. Everything logic-wise is using Python, so it's suggested to start with installing the requirements. Of course, we need to run our Docker stuff, so Docker compose up and then -d is in detached mode, so it doesn't show you all of the stuff that it's doing in the window, in the terminal, in the terminal. And then what have we got next? So I have done this already. Everything is running in my local instance of Docker, so that's nice to know. And with our Docker compose up, oh yeah, now will be the time to go through what we've got here exactly. So each service is based on an image in a repository. These Bitnami are a fairly well-known like registry provider, company that maintains Docker images. So we're pulling Zookeeper and Kafka from them, making ports available within and externally to our thing, externally to Docker, so we can connect or not, depending on how we've set them up. So for us, to connect to our Kafka thing, we'll be using the port 9093, specifically that one. Yeah, for the Zookeeper client to check on this, we then have the connect here. So then that's also based on a port. So that's the Kafka setup. Trino is very simple. The company who makes Trino maintain their own images. We need to make a port available for us to connect to Trino, because that will be the client that we're doing with. And because Trino includes logs, it's good to specify a volume where you can access the logs if your container or image is having problems. And then this is our console, our Red Panda console. Yeah, essentially it's just an overview of what's going on. Main thing is to make sure that the Kafka brokers connect. Red Panda is able to connect to the Kafka brokers, and that you can then access. 8001 is where you'll then access this console, and we'll open that in a second to see what's going on. And yeah, this is our Postgres setup, including the ports, so you can still access it. And in this instance, we're creating a user password and a database in environment variables, because we need to be able to access Postgres through Trino. So yeah, in this instance, our connect strings will be based on these username and passwords. Okie doke. They're the main important parts of all of this Docker Compose file. And when you run Docker Compose up, it is the equivalent of building and running this whole setup, which will then mean you end up with something like this. Cool. Let's first look at our Red Panda console. This is what that looks like. Yeah, this is what that looks like. Let's in fact explain what we did with the what's it called? The Kafka topic first, actually. Excuse me. So to enter and mess around with what is in our Docker, we can Docker exec into our things, and we're in this instance using Bash as our terminal program. In this instance, it's necessary because it's necessary to create topics, a topic in this instance, excuse me, within our Kafka thing that we can then connect to our Trino setup. In this instance, all of that stuff is in this directory. This is standard from Bitnami, by the way, so if you ever use this company, then generally it will be an opt Bitnami, and then the thing that you're using, and then the bin. The bin here is just all of the shell scripts that you can use to do stuff with, in this instance, Kafka, but in other instances, whatever program you're running. I've already created the topic, but if you do this, you will get in fact, it doesn't really matter because I'll just get an error saying it exists already. Yep, there you go. But in any case, when it doesn't exist, you'll get a successful, we've made this for you. If you run this from scratch, there of course will be no messages there at the moment, but because I've run this before, we can use the consumer script, to have a look at our messages that we have. So here we're just saying run a Kafka consumer with the topic power data, and then do it from the beginning. So this means that any time I've ever put any information in, so you can also see how long it's taken me to get this right, and it only goes back to the 30th. Well, in any case, okay. I promise I only worked on this yesterday. It's not quite true. And then let's get out of that. So in total, I've gone through 3,905 messages so far. So that's nice. So once you've done this, then you have your Kafka topic set up, and you're able to consume from it. Let us then exit the Kafka container. And we need to make sure that the necessary tables are there in Postgres. In this instance, we're using just a direct connection to Postgres. You could also do this via Trino if you wanted to, but I was, in fact, I don't know why I chose this. But essentially we have a Postgres connector. In Python, we're using the Trino username, which is then the Trino password as well. Our host is then our local host. The port that we set up in our Docker Compose, essentially these should all match Docker Compose to be clear. So the user and password are there, and then our database is there. And then the port that we're referencing is there, and we know that we're running locally. Where have we gone? We know that we're running locally, so it will be on localhost. So that's the setup. For more info, you can check out SQL Alchemy and then the Postgres connector. It's fairly comprehensive. So that is how the connection is made, and then based on that, you can do you can run execute commit statements with a with statement as the connection. In this instance, I'm creating tables based on models. SQL Alchemy, the joy of using an ORM is that you can just specify exactly what you want the table to look like. What am I saying? Exactly what you want the table to look like, and then based on that you can run select statements, inserts, whatever you like. So in this instance, this is what our table will look like. It's a table called Anomalies table. It has the different electrical phases. So I should have given a quick talk about that. It's all falling to pieces again. Phases in not menstrual cycle, none of those. In electrical smart meters, please. It would be a lovely thing for me if you have a good image for this. Kind of, I guess. It's not really. I mean, it's okay, isn't it? Essentially, for every meter, all the new meters, at least in the Netherlands. Then, excuse me, I should have said that where I'm coming from. You have 3 different cables that make sure that you have energy in your house. This is for a couple reasons. One, if one of them goes, then you still have energy. But also it's then, dividing the, what's the word? The strain on the network, essentially. So all the new ones will have 3 phases, which is essentially just 3 different wires. And all of the old ones are single phase, single wire. So if that goes, then you just don't have any power. In this instance, we're running mock data on kind of assuming that we have 3 phases. So essentially, what we'll have here, when we'll see this in the dashboard, but in the Netherlands, the voltage mean is 230 volts. So on average, this is what every plug, socket, and thus also meter should show. This is the average, but then the range that it is allowed to be within, according to, I guess it's a governmental standard, is between 220 volts and 240 volts. And for us, anything out of that versus any weird change in the time series in a short period, we are going to consider outliers. And then based on that, we'll have various different predictions. So these will all be Boolean. So is it an outlier? Is it not an outlier? And then we will have the timestamps of when it was, when the thing occurred. Cool. So if we go back to this script, essentially we create the tables if they do not exist, and if not, we throw the exception that they don't exist. That's about it actually with this thing. I was playing around a bit with different select statements and stuff. So here you could run this. In fact, let's do it. Why not? We're doing a demo, aren't we? So you may as well. So because I've run this previously, I know that there are some anomalies in this table. Let's get the anomaly one and not the example one. I can't spell anomalies. There you go. Cool. And then based on this, we then have a pandas data frame of previous anomalies that we had. So in this instance, we were manually putting in a anomaly, and then our hard cutoff is anything below 10.5 or so. We then get it's considered an anomaly. But there was also over various periods different things that were considered anomalies, which then someone should look into whether or not they are actually anomalies, whether or not we consider them problematic. This is the only anomaly detection algorithm that is included here, apart from the half-space trees, but I didn't tune the half-space trees very well, so it's often just not thinking it's a outlier. But yeah, so this is the only one that is taking time series, the fact that we're looking at time series into account, and it, in this instance, is the only one that thought it was an outlier, because these other ones are not inherently looking at how the change in the time series is. So it's likely that if before and after this moment there was rapid change in our time series, which could be interesting to know. And then for the rest, yeah, I mean, where we have extremes, so 240, for example, we are likely to have some of our anomaly detectors saying that we have outliers. But yeah, so that's the general table. That's what we've done before. It's more interesting, I think, to see it fully online. For if you're running this yourself, then all you need to do is run this Python thing in the terminal. So just that, because I've done that already. In fact, it doesn't really matter, right? Because it'll be there. Yeah, example table already exists, and blah 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 already exists. Yeah, so that's all wonderful and groovy. But if you've not run this before, then these tables will actually be created. Yeah, so then that basically means we're good to go with regards to the setup for the dashboard. All I've done here is write a main script that runs both the Kafka stuff, so a producer that will then produce from our example data. It will just spit out something at random. Well, at random, it will choose randomly and then spit out a new time and whatever the value was at that point in time. And then I'm also running the streamlit dashboard as a separate process coming from this main py. All of these are done using multi-processing, by the way. So on your local machine, it will take one core to run the producer power stuff and another core to run the dashboard. When I talk about cores, sorry, I'm talking about, how do you say core in a different way? Essentially the processing things that your computer has. So in this instance, we have a Mac Mini, which in general has 12. And for the most part, they will be spread, whatever you're trying to do will be spread across different cores. In this instance, we're just saying use one of these to do this process. So that's all that's happening here. This means that you can run multiple things in parallel in one script. So for the dashboard, I want to constantly run that with, so we can interact with it. But I also want to constantly spit out, every 5 seconds, another Kafka message. So, we're reaching moment of truth stuff, I would say. Shall we then run our main.py? So, this will spit out the front end, and then, ooh, that's fun. It's New Year's, so I apologize if you're hearing fireworks and stuff in the background. So here's our dashboard. Every 5 seconds we should get a new dot. So that's fun. Everything in this top plot is Trino interacting with the Kafka setup. So just so we can show off our red panda thing, because I opened it and then forgot about it a little bit. We have these being our measurements, so at 54:42, let's say. Jeez, I'm not used to talking so much. So yeah, whatever I just said, something 42, 54:42. We had a message. It went into this topic. And where were we? 54:42. So then this is our message. It has then a timestamp of the thing that we had, our L1, L2, and L3, which then we also see in our front end. Where were we? 54. Yeah, so this one. So these values that are plotted here are then, this then gives an overview of that. Yeah, and then also you can look at your consumers. As it stands, we don't have any Kafka consumer set up because we're using Trino. So that's interesting. These are the various partitions. I'm only running Kafka on one container, so there's only one partition. What else? This is the general configuration for the setup. So this is how long the message will stay in the broker, for example, and various other things. Just a general overview of how this works. I think that's about it, really. Cool. Useful for when you're troubleshooting, I've got to say. We can get rid of that. This was then our outlier stuff. Cool. We're slowly getting in our mock power data. As things are going, that's looking pretty nice. So as it stands, we've had no anomalies. It's fluctuating between just below 230 and 235-ish. So all of this is fairly regular. But let's say we want to add an anomaly to see if our outliers are doing their job. So we have this huge outlier now in our L2. It's 210. And our anomaly detection algorithm has picked up that this is an outlier. It's below our hard cutoff, so our hard cutoff one has indeed caught it. Half-space trees continues to be useless. I should probably have put more effort into tuning that. And all of our other outlier prediction stuff has caught it as well. What's interesting to note is because this is a hard cutoff in one direction, if it's above 240 in this instance, we will not catch it. If it's above, 240, as I say. So if we said, let's throw in 300, if you have this much voltage in any of your things, then you will have a fairly big problem. And there it goes. So we've added a 300 in, but it's not below our hard cutoff, so we don't expect to see, which we indeed don't, we don't expect to see that our hard cutoff considers it a outlier. But all of our trained model ones, consider it an outlier then. Apart from half-space trees, should have done a better job there. That is it, kind of the dashboard itself, which is kind of the summary of it. We'll leave it running to see if there are any more organic outliers, because we're adding mock data that has some interesting qualities to it. Possible that we don't get it because we're just streaming from random data sets. I wanted to kind of show you how you can then manage your Trino setup. So Trino has three different ways that you can interact with it. One is just using the user interface that they provide. Because this is localhost, there is no password to it, but if you want to deploy this in production, there are ways that you can set up various different passwords. This is what we end up having. This is our cluster overview. These are all the different SQL statements that we've been calling to make sure we have data in our front end. And you can kind of see it go as it's going. So to check our, what's the word I'm looking for? To include the anomaly stuff in our front end, we're just saying, give me all of the anomalies where the timestamp is bigger than the current timestamp minus a certain interval. With regards to Kafka, where am I? So these are then the insert statements from our anomaly detection stuff. So this makes sure that it's in the table below the plot. This inserts the anomaly when it occurs, and this is a select of the from the power data as Kafka is streaming it in. So we will only see the last 10 minutes of Kafka data. God, keeps jumping. Of course, I'm doing too many things, but what's good to be aware is that Kafka defaults to UTC. So in this instance, we need to have an interval of 70 minutes. So it's 60 minutes ago to put us in the right time span, and then 10 minutes to only give us the last 10 minutes of the data in this plot. So at the moment, we're still less than 10 minutes, but once we've hit 10 minutes, we will start seeing that it begins to scroll. We also see that we do have some interesting example data. For the most part, it seems you could possibly argue that the Gaussian scorer is over-predicting, but I mean, this at the moment is going over 240, which is outside the range that we want. So it's perhaps not too terrible that it is doing that. The one-class SVM is also picking it up sometimes, as well as the elliptic envelope. But yeah, it's interesting to just see it go. So we know for certain that these are outliers, but this is just coming out of our mock data. So it's possible that this is, it's possible it's not, but in any case, in a production environment, you would probably want to look into why you're getting such high voltages. Yeah, so that's cool. And yeah, I wanted to dive in a bit more into the clusters. So this is a general overview of what's going on. We see a peak every 5 seconds or so because our front ends are based on every 5 seconds. We can look more into our workers, so we're only using running one container. So we will only have one quote-unquote worker in this instance. And so this is then the active plot of what's going on with regards to CPU, how much memory the thing has itself, but all it is doing is just running different queries, so you should never really have tons of heap memory necessary. What else? That was the workers list. These are then the running queries as they go. You can then dive more into the query itself. So who did the thing? So we're using SQL Alchemy to run a select statement, the users and the admin one that we created. And then these are various splits. So like how long did it do to make all these things happen? So here we have total time spent. You also see the starts and finishes, which is quite fun to see as they go. These are then the amount of rows per second, which is a nice statistic to have, maybe. So you can also dive into more in-depth information about the query itself that was made. So in this instance, this is one of our select ones. We can then look at the scheduled time, the CPU time. It goes very in-depth on what happens in this query, essentially. So as you get more and more complex ones, then it's easier to see. To see where certain things are taking more or less time. So then this is the amount of rows per second, because it's going very quickly. It's then quite large. The amount of time it took, so 5.86 milliseconds to get this query done. So that's nice. And then more general stuff. So to run the query itself, it has essentially 2 steps. There's a table scan, and then the output depending on whatever the columns and select and etc. were. And then the general overview that we saw. The stage performances is also nice to know. So how long did each part of the 2 operations that we just saw take? What the outputs were. General stuff. And then the splits are always fun to see. So we started at 1804.07 and 698 milliseconds or so, and then we ended in the same second with 705, and then various different splits within them. So you can get incredibly in-depth detail on what queries are being run on your table. On all of your data inputs essentially. So the one that we were just looking at was Postgres, but you have exactly the same with the Kafka Power stuff. All of it is running the same sort of idea, so it doesn't really matter that this is streaming, and it doesn't really matter that the other one is a relational database. So that's one way of interacting with Trino. Where are we? Shouldn't have put myself in the middle, huh? Another way of interacting with Trino is using the CLI that it comes with. Because we're running in Docker, we need to Docker exec into it. This is then the command that we're using. This is the name of the container. So power anomaly detection Trino 1 is power anomaly detection Trino 1. The server we know is running on 8080 because that's what we set up in our Docker Compose. And we have a catalog called Kafka. I'll explain the config a bit more because there is some level of configuration needed to get Trino to be able to talk to all of the different things. But in any case, we have set up a catalog called Kafka, and then we made a schema called Power. So we are essentially saying execute the Trino bash CLI with the server that we made with defaulting to the catalog that we care about, and then the schema that we care about. So let us do that. So here we've got the CLI, and then here they very nicely remind us what our schema is. We can then run things like show catalogs. So in this instance we have configured Kafka Postgres. I was also playing around with the local file one and system to see what you could do with it, but in our instance we will only see Postgres and Kafka. And then you can run the selects or whatever that we saw from earlier. So this is then all the anomaly stuff, and then you get it. It's using a CLI called less, L-E-S-S, to show the output. So in any case, we essentially have markdown tables showing the things that we care about. Booleans and whatnot, our timestamps, our different L's at each point. And you can then just scroll through this with enter, and then when you're done you can press Q, and then you'll come out of it. And then we can do our select statement from Kafka, for example, which is then using the schema that we've used, but then also the name of the table, so power data. Because we've previously specified our catalog and schema, in theory we should also be able to get this info from just requesting the table, but for my memory it's always handy to specify which ones you're doing. Wow, they're really going with the fireworks, huh? So yeah, this again is similar to the tables before. You can use the arrow keys to kind of navigate through these things. I really hope the fireworks aren't picked up super loud in the recording, but I got to imagine they probably are. And then so the way that Trino deals with Kafka, there are kind of two ways that you can do. One, you can say, give me all of the information from Kafka as well as the message itself, or you can say just give me the message itself. But what I would usually suggest is to include the stuff from Kafka as well, because it will then give you the timestamps. So as good practice, you should probably include the timestamp in the message. You never know if people are doing good practice or not up until it's often too late. So in general, I would suggest configuring to give everything and then dealing with the message itself in your program that you're interested in using. So that's there. And then last but not least, you can interact with it, of course, in Python, which is then what we've been doing with everything. Here is an example of the setup I've been using. This isn't the most nicest way of doing SQL alchemy stuff, but essentially we're just saying here is the SQL that we want to run, and then shove it in a text thing and then read it in as a data frame. So that's another way of doing it. This, by the way, is then using SQL alchemy with the Trino connector. And so for that, it is that, and then this thing, which is then also managed by Trino as far as I understand. So that's also nice of them. Including this means that you're able to then get your, where have you gone? To get your connection to function as expected. So if you don't have this, then it will have no, SQL alchemy will have no idea what you mean when you say, give me the Trino connector. Yeah, wonderful. And then last but not least, this is DBeaver that we saw earlier. This is a fairly general means of talking to different SQL things. But again, we see the same SQL commands to then see the outputs. So these are then our our messages from the last 70 minutes per UTC. So then 10 minutes ago. Yeah, indeed. 12 and then 2. Yep. And then these are all our anomalies. Then with our V or not V, as it were. And then the specific things, and I mean, we've seen this info before, it's just another way of doing it. And then yeah, so that's where we are, and then this is based on this connection. The DBeaver itself should come with a Trino connection thing, but if not, then you should be able to download the driver, or it should prompt you to do that. Yeah, and then this is similar information as what we saw in Python. So the username we're arbitrarily taking is admin. Trino in this setup doesn't have any password, so you can just leave it blank. We're running localhost, and then we also specified port 8080 in our Docker Compose. Yep, so that, and then you end up with this connection. Wonderful news. Yeah, so I guess that's... Oh, shit! It's not it at all. I, of course, forgot the Trino setup. I should explain that. So, Trino is essentially a Java program that requires some level of configuration to run as you want it to. The way that this is done with us is with a set of .properties files and config files. The initial one... Well, these two you can kind of do to your heart's content a little bit. If you go to the Trino website, they will give you what they suggest as setups. So you get started. This is what we've done. So spin up Trino on Docker. Where are we? Configuring Trino. So they do some default stuff. But yeah, where are the examples here? Deploying. Yeah, so these are then the main ones that you can care about. So Node is being used. The JVM. I'm not very good with Java, but yeah, there we go. Java Virtual Machine setup. In general, most of the defaults should probably be okay with you, but I was dicking around a bit, so I've specified. I don't think I did anything with the Node one because the defaults for that were fine. But yeah, just various things that you can set up. So in this instance, its maximum is 4 GB that the server can hold in heap memory, which we saw I think in the UI and yeah, some other minor things. So what happens if there's out of memory? Well, what happens on XYZ? It's nice to configure these as you like, but for the most part, the defaults will probably be fine. In this instance, it is important to do. If I remember correctly, it will assume a lot of these things anyway. Oh, that's not true. The discovery URI is an important one. It's... Lord, they're really going for it. This is essentially what you need specified to where you connect to it. So because we're running locally, we are using our local host, and we have specified 80 as our environment, as our port. Yeah, but essentially they're not too in depth. You can also specify whether or not you want to include the coordinator or just the workers. We want both, so you have both. But yeah, that's about it for the config. And then per catalog, you will need to do some configuration. You can find most of the information necessary on Trino's connector thing. I had this open already, didn't I? Yeah, there we go. So in this instance, we've used Kafka, and so here they give you all the different options that you can configure. But for the most part, these are the ones that you need to be caring about. So in this instance, we set up our connector name, as we said. We specified where the nodes are presented internally. So this is then our 9092 that we saw in our Docker Compose here. It's specified, so the internal connection from here to from here to here is then using this connection, which is then our host. So something called Kafka : 9092. So that needs to match. If not, then Trino will have problems finding Kafka, essentially. And here Trino likes it when you specify the schema and then the table name. So in doing this, we have power as our schema and power data as our table name. And you can also see this here. So you've got Kafka as our catalog, we've got power as our schema, and then our table we've got as power data then. And then this is what I mentioned earlier, the internal columns, do you want to hide them or not? So if you specify false, then you will get all of these like underscore ones, so pretty much everything apart from, all of them, but you will get everything as an underscore column. So then also your timestamps that you maybe care about if the person that's sending it has not correctly done their message. If you set this to true though, Trino will attempt to unpack what your message is. So instead of having all of these columns, you'll just end up with columns that correspond to the message itself. So you'll have timestamp L1, L2, L3 in this instance. Up to you. That's a config thing. I suggest to not do that, but unless you're very certain that the timestamp is included in the message. If not, then I would set it to false. And then you can also specify on top of this where the configuration properties are themselves, but the default is probably fine. You don't super need to mess around with where things are being saved in that instance. So that the local file was me messing around. This is all that you need for the local file, funnily enough. And then you get this. Essentially just all the logs that happen in the local machine. So in this instance, there's just a bunch of HTTP and curl requests, between Trino and all the other things. So it's kind of nice to see that real quick as well. Not super part of this tutorial though, so we'll ignore that. And then last but not least, we have our Postgres setup. So the connector is then Postgres. This is the URL. This is Java database connector, is what that stands for. We're specifying that it's Postgres, and then we have a user called Postgres and a port called Postgres, and then our database that we care about. This was then also what was included in our Docker Compose. So, oh no, that's not quite true. How have I done that then? Postgres. Oh yeah, excuse me. So that is then the connection, excuse me, and then you then specify your user and password on top of that then. So we're using Postgres, and then the table is called Postgres, and the port is then what we specified in Docker Compose. There we go. Goodness me, we got there in the end. So it's that slash that is basically what we've done there to get to this, and then the general like setup of the connector is that you specify that it's a Java database connection, because that's what Trino is written in, and that the database that you're connecting to is PostgreSQL. You also see this in DBeaver as well if you try to make a connection. So now real quick, I'm probably going to get sidetracked, which is not really what we want in life, but yeah, a lot of programs are also using Java database connections. So then here we've got the specifying that we're using that type of connector. We're using PostgreSQL in the same setup. Our table, like the default that a lot of people that is used, excuse me, is Postgres. The default for where the port is 5432, and then in this instance, it's assuming that we're running on localhost. Because we're running in our container setup, that's not the case. We're running on this endpoint, so specifically here. So that's how we get to that config. Yeah, and then assuming that all of these connectors are set up correctly, then everything should be able to talk to each other. So that's about it, really. Maybe it's nicer to dive into as well how we made the data. In this instance, it's a very simple random forest regressor. We had the data that I was getting out of smart meters. We do some level of just general cleanup, so making it into things that we understand. Making the timestamp as a datetime variable in Python. Removing anything missing in the indexes, setting the index to the timestamp. Oh yeah, I was looking at normalizing, but it wasn't inherently necessary, so these last two are not super necessary, but it's fine. Yeah, and here we're just using a regular SQL sklearn model. And we're just saying if there are anything missing, then fill what our average should be, and then shift 1 down. So essentially get the table and then move everything down 1. So we're comparing our X to our Y, and our Y is just the same as our X, but then lagged by 1. So we're predicting the previous, the next step based on our previous step. And then we're doing the fit, so previous to next, and then our predict is then just spitting out the predicted data frame again. Yeah, and then we do some plotting, and then we save the model so we can use the model to make new data, which is then what we'll find in our example data things. It's based on 3 separate meters, and yeah, it's then fake data that is based on real data. Cool. And then last but not least, a bit of a dive into the anomaly detection stuff. Here is our river anomaly thing, and then here are different sklearn models. All of this is based on the example data that we created before, just kind of stacked together. Nice. And then, yeah, the train test setup is just then based on this Python function. So what we'll, in fact, let's just run through it, why not? So import all of the things that we're going to use, and then here's the data frame that we're working with, so similar to what we were plotting in the dashboard. Here is our main function, so plot the time series that we're training on, do the different training things, so there are slightly different methods that are used to train the different things. So Gaussian scorer had a specific way of doing things from River, sklearn, all of them assumed this model fit, and then for other River things, then it was using this setup. So none versus not, and then various dictionaries, etc. After the training, you can then dump the model. So this will then spit out all of the different pickle files that we've been using. Pickle. And then here we're manually adding some outliers to see if they'll be caught. We're plotting the new setup, so the data, but then also with the outliers in it. And then we're selecting our outlier data and seeing whether or not our models that we've created, the model that we put in, that we're creating, catches them or not. So yeah, let's do that. And then here is the default. So this is then the Gaussian scorer with a grace period of 50. Grace period in this instance is wait for at least 50 time points on your time series and then start looking into different outliers. So this kind of assumes that the first 50 are good, so not anomalies. Yeah, here we see. So our last meter, you can kind of see them stacked, and you kind of guess where the stacked nature occurs. We had 2 meters that were kind of doing, what you'd expect, kind of bumping around a bit. You have some things that maybe are a bit outlier-ish, but in general they're around the same area, and for the most part the phases are doing kind of similar stuff. But then this last meter that we had the L2 and L3 kind of doing similar stuff, but then for some reason the L1's being, what's that, like 5 voltage lower on average, let's say, which is then maybe interesting for the anomaly detection to pick up. And then in this instance, similar to our front end, we're manually adding anomalies that are then below a certain point to then see if the outlier detector that we're using, which is then in this instance the Gaussian one, to see if it pulls them up. And the way the Gaussian one works is essentially a percentage. So between 0 and 1, how likely is it that the things that you put in are outliers? In this instance, it's almost 100% because of how far away they are from the setup, but you can, what's the word? You can tweak this to the thing that to what you care about, to some extent, to what you care about, to the level of, what's the words I need? The level of cutoff that you care about. So in this instance, it's almost 100%, but maybe you want to flag outliers that you think are, maybe 50-50, where you're not 100% that if it's an outlier or not. Or maybe you want to do it a bit more conservative and say 80% or something like that. In this dashboard, I believe my default is, so 90%. So in this instance, if the likelihood is above 90%, then it will consider it an actual outlier in the dashboard. So that's looking pretty promising for the Gaussian scorer. And then we can also try out one of our sklearn ones. This is then the elliptic envelope again. We've got our initial, excuse me, I need to run it again because I overwrite the plot data. That's not very clever of me. Oopsie doops. Oh no, I overwrite the df in fact. Learn from my mistakes, that's bad Python coding, kids. Essentially, if we run that again and do it from scratch, we should be fine. Always good to plot your stuff as well, because then you see these very quickly. This is then the data we're basing on again, and then this is with the outliers, and then the prediction for the outliers. The way the sklearn model stuff is set up is if it's a 1, then it's considered not an outlier, and if it's -1, then it's considered an outlier. I don't know if I need to show proof, but I feel like I need to now. So, I don't know. Where would they say this? Just in one of them, I guess. We're talking about the elliptic envelope, so let's go there. Where are we? Attributes, parameters. Yeah, there you go. So predict returns 1 for an inlier, which is a gross word in my opinion, and -1 for the outlier. So in this instance, you can just say if your response is -1, then it is indeed an outlier. So true to then be your outlier. A bit of a shame with the sklearn ones because there's no. Well, I mean, no. A lot of it is not. What's the word? It's not. Yeah, there's no probability to it anymore. Like likelihood of it being an outlier. Although you can have, for some of them, I think you can have predict prober, which is nice to see. One inlier, one out. Yeah. Although to be fair, this isn't probabilistic. It's just hard cut off on covariance. So me looking for probabilities is probably not that useful. Where are we? I don't know. I think for the local outlier factor and maybe I think the SVM should give us probabilities if we ask for them. Wow, really? No. Yeah. Okay. Well, decision function. Yeah, I need to look into this a bit more, I guess. But oh yeah, raw scoring function of the. Yeah, so in theory, this should then give you output of not just yes, no. So your -1 ones again, but various different scores of how much this is probably an outlier or not. Right. So we've done more of a deep dive. I hope this gives an overview of what you can do with Trino. It's also fun that we have streamlit, I guess. Let's just add another outlier for the road. Yeah, I think nice overview. Got outlier stuff. We've got some anomaly detection, which is a bit of ML. We've got some containerization going on. Fairly comprehensive project, I think, to get you started on a lot of different things. We've done streaming data, we've done relational databases, we've done semantic layer to talk to the different things in the same way. We're doing some Python coding using SQL Alchemy and the streamlit front ends and model trainings. Our pipeline is then using the containerization, like we were saying. Yeah, fairly comprehensive, I think. I flew through this perhaps a bit more than I maybe should have. If you're curious to know more about certain aspects of this project, let me know. I'm always open. And yeah, I hope this was useful. I look forward to seeing what people do with this, and yeah, I'm curious what the outcomes are. Have a lovely evening, morning, day, and till next time.